Okay, so before we look at the giant covalent structures, you need to be absolutely clear in your mind about simple covalent structures. If you're not, go back and check. So for giant covalent, we're going to just consider carbon. It happens to be a really good example, and you know that carbon has got 4 electrons in its outer shell. It's in group 4. If I draw another carbon here, carbon, and I show these electrons with circles, then we've got over here, we've got our covalent bond. But you can see here, there are opportunities for carbon to bond in exactly the same way. And carbon is very, very unusual in that it's very keen to bond with itself. So what ends up happening is this. Something like this, and the idea is that it carries on bonding. If you've got plenty of carbon around, it carries on bonding. Theoretically, there's no end in sight for that structure, and that's where that phrase that we've got here, giant, comes in. It's a never-ending structure. So, just bear this in mind, carbon is very good at bonding here with itself over and over again to form this giant network, this giant covalent structure. Let's have a look at what that might actually look like in 2 or 3 key cases. So we're going to look at diamond, and you remember from the previous slide that carbon has the opportunity to form 4 covalent bonds because it's got 4 electrons in its outer shell, and at the end of each of those bonds is a carbon. Each of those carbons in turn is able to form 4 bonds. So here is a carbon with 1, 2, 3, 4 bonds. Here's a carbon with 1, 2, 3, 4 bonds. Here's a carbon with 1, 2, 3, 4 bonds, and it goes on. Now, I've actually drawn my diagram incorrectly because this carbon here only has 2 bonds at the moment. It's incomplete. I'll pull up a photograph, an image from the internet now, so you can have a look at what it looks like. Hopefully you'll be able to see each of those black dots as representing a carbon atom here, and you can see the 4 bonds. Carbon, 4 bonds. The ones, like I say, that don't have 4 bonds actually do, it's just that the structure is unfinished, so it's a very simple representation of diamond. That's one format, one type, one way in which carbon can bond with itself to make a big structure. Let's have a look at another one. So the structure that we're going to look at, the name of it is graphite. It's the stuff that's commonly found in pencils. Let's have a look at the structure. And here we go, this is what the structure looks like. You should be able to spot lots of hexagons, 1, 2, 3 hexagons, and of course the structure goes on. So wherever we've got a carbon with just 2 bonds, it has an extra bond, it just needs to be drawn on. And so it continues. And that's the interesting question, because when you refer back to earlier in this video, carbon's got 4 electrons in its outer shell, so it expects carbon to form 4 bonds. In this case, in graphite's case, carbon only forms 3 bonds, 1, 2, 3, which means it's got a spare electron. Let's have a look at a slightly different diagram for this one. So here's a diagram of graphite, and you can see a flat layer here of hexagons all joined together. Each of these represents a carbon, and there's the carbon with 3 bonds, carbon with 3 bonds, carbon with 3 bonds. Remember, the carbon with 2 bonds, the structure goes on. So carbon's got 4 electrons in its outer shell. Here is where it's formed 3 covalent bonds, 3 sharing sets of electrons. And remember, for each carbon, they've got 4 electrons in their outer shell, there must be a spare electron. And those electrons float around in here. Let's just pause on that one and refer back to carbon here. So 1, 2, 3 electrons are used for this carbon in terms of bonding here. 1, 2, 3. There's an extra electron which is free. It's not used for bonding, and that electron floats around in this layer here. So the idea is this structure here, this sheet of hexagons, is laid above this sheet of hexagons, is above another sheet of hexagons, again another and another. So you've got these layers of hexagons. And on those in between those layers, here are my layers looking at from a side view, and in between we've got electrons here that are free to move, and that gives carbon carbon in the form of graphite, a very distinct property which we'll look at now. So what we're now going to do last of all is compare the properties of diamond and graphite. First of all, with diamond we've got lots and lots and lots of strong covalent bonds. So diamond's got lots of strong covalent bonds, therefore it's going to have a very high melting point. It takes a lot of energy to break up those bonds. And remember, graphite has also got lots of strong covalent bonds, so it's also got a very high melting point. For graphite, the sheets don't have strong bonds between them. That means those layers Each layer individually is intact, but they slide across each other because there aren't strong bonds holding those layers together. So the layers can slide. Diamond, on the other hand, only has strong bonds. It has no weak bonds like graphite does between the layers. So if diamond only has strong bonds, it's very, very hard. And in fact, you may well be aware that diamond is the hardest substance we know. The last point is to do with electrical conductivity. With graphite, remember, between those layers we had electrons, and those electrons are free to move. Because those electrons are free to move, they can move left to right in between those layers, and that's why graphite conducts electricity. So the electrons are free to move between layers of graphite, which means it's an electrical conductor. And with diamond, there are no free electrons and there are no free ions that are free to move. So diamond is an electrical insulator.